Hello and welcome to comp452 computer architecture. Let's extend our data path to uh, accommodate execution of load word and store word instructions. Now load word and store word instructions are I-type instructions. Okay, and branch is also an I-type instruction, but first we will extend the data path for load word and store word, and after that we will add the functionality or we will add the pieces to execute branch if equal instruction. All right. Okay, so what you see in front of you is the data path that was complete for R-type instructions: add, subtract, and, or, nor, and SLT. Okay, so these R-type instructions have two register values that are operands or inputs to the ALU, and the result produced by ALU goes to the destination register, which is specified by its number in the RD, this RD input of the register file. So this is a 5-bit number, 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 and this is a 32-bit number. This is 32-bit, this is 32. Okay, now it's very important that you guys should write, or you should know how many lines are contained, or how many signals are contained in one line. For example, this one line is 32 signals. This is apparently one line, but actually this is a 32-bit number, so therefore 32 signals. Oh, sorry, not 3R, but 32. Okay, so I'm actually going to erase these numbers because I'm going to be needing this space for writing some important stuff. Alright, so now we want to add pieces for load word and store word instructions. Now these are I-type instructions. So I-type. Now let's quickly go through how load word and store word work, and what is the instruction format of load word and store word. Actually, why not use this space? In load word or store word or I-type instructions, these 6 bits are for opcode. Then we have 5 bits for RS. Then we have 5 bits for RT. Okay, so, and then we have 16 bits for a number. So these are 6 bits, 5 bits, 5 bits, and 16 bits. Now for load word and store word instructions, this field, this 16-bit field, contains offset. It contains offset. Okay, and this 16-bit field contains this 16-bit this 16-bit field contains a number in 2's complement format, 16-bit 2's complement format. Okay. Now let me give you an example. Yeah, I'm actually talking about load word and store word only. I'm not talking about branch instruction. I'm not talking about add I or sub I or and I or I or nor I or SLTI. No, I'm not talking about those instructions. I'm just talking about load word and store word instructions. They are also add I, sub I, and I, or I, etc. These are also I type instructions, but their data path is slightly different, so we're not going to go into that detail. So we will just focus our discussion on load word and store word, and then later on branch if equal instruction. Okay, now let's quickly write some stuff here. What does load word do? Data memory to register transfer. Data memory to register. That's the direction of data flow. Store word, what does it do? Register to data memory. Okay. So now, what is the format? The format is this: load word. Okay. Here we have the register which is going to receive the value read from memory, comma, offset, parentheses, RS register. Just to give you an example, we could have load word $7 and $8.10. And this could be one instruction. This is just an example. So let's see what this instruction is supposed to do, or how this instruction is supposed to be executed by MIPS processor. Okay, so first of all, this instruction, what it will do is it will get the value in register 10 to add 2's complement offset to it 3. Send the result to address input of data memory. 4 get the value output by memory and store it in register 7. this is what it's going to do. Now what is the offset? I forgot to write the offset here. Let me erase this much only. Add 2's complement offset, which is 8 in this case, to it. Okay. All right. Now there is a problem here. There is a problem here that offset is, we want to perform addition operation. Look, we want to perform addition operation. And to perform this addition operation, we will program our ALU to perform addition. Okay. So the value stored in RS will be coming to the upper input of the ALU, but this offset should be coming to this lower input of the ALU. It should be coming to the lower input of the ALU. Okay. So the question is, offset is 16-bit, this is 16-bit, but ALU input can only be 32 bits. It cannot be 16 bits. It has to be 32 bits. This register value, we already know that it's 32 bits. So the other important point is that this offset is contained in the instruction code itself, from bit 0 to bit 15. So, but we want to convert this 16-bit value to 32-bit value, and since this offset is in 2's complement format, so we need to preserve the sign of the number. And we know that in 2's complement format, if most significant bit is 1, then it's a negative number. If it's 0, then it's a positive number. So this means that we need to look at the most significant bit of the offset, which is bit 15 of the instruction code, and simply replicate it. Okay. And this hardware is called sign extender. So this means that a part of this instruction will come here. Actually, I should have been more careful. I'm going to erase this stuff here. I'll rewrite it, don't worry. That's the problem with drawing here. On whiteboard we have a lot of space, so we don't worry. Let's quickly write here. Load word is mem to register, and store word is from register to data memory. It's data memory. Okay. So the lower 16 bits, they come here, and here we add a piece of hardware and we call it sign extend. So the input is 16-bit. These are 16 bits, but it outputs a 32-bit number preserving the sign of the input number, and then that number goes to the second input of ALU. Okay, so you see that here we have a point where two different values are coming together. Here we have two different values coming together, and one of those values will be going to the lower input of ALU. And this sign extender is a combinational circuit that converts a 16-bit number to a 32-bit number by preserving the sign. So what does the sign extender do? It's very simple. It's very simple. Sign extender replicates bit 15 of instruction code in the upper 16 bits of its output. Lower 16 bits are same as input. This is so simple. For example, if the offset is like this is 2-byte number, and here we have, let's say, A, B, C, D. This is a 16-bit number, A, B, C, D. Now A means 1010, B means 1011, C means 1100, D means 1101. Now look, this MSB is 1. This most significant bit of the offset is 1. So this means that sign extender will give you this one will be replicated here, and you will get 1 1 1 1 1 1 1 1 1 1 1 1 and 1 1 1 1. This is what the sign extender will do. Now let's suppose that instead of this, if we had number like 3F 3F EE, 3FEE. Now this 3 means 0011, F means 1111, E means 1110, E means 1110. Now what the sign extender will do is, it will look at the MSB. MSB is 0. So you will have a 1, 2, 3, 4, 5, 6, 7, 8 zeros. Then 1, 2, 3, 4, 5, 6, 7, 8 zeros. So this number will become F, A, B, C, D, and this number will become 0, 0, 0, 0, 3, F, EE, 3FEE. So this was the offset. After sign extension, it became FFFFABCD. Why? Because A is 1010, so this makes MSB 1. So MSB is replicated in the upper 16 bits. Now in this case, this was the offset, and 3 is 0011, so MSB is 0, so 0 is replicated in the upper 16 bits. So this is what this sign extender does. Okay. Now the other thing that you can immediately see is that there are two values coming together at this point. So we already know that there is going to be a multiplexer here, and this multiplexer is going to be a 2 to 1 multiplexer. Since both values are 32 bits, this is 32-bit value, the value coming from register is 32-bit value, so we will have a 32-bit wide 2 to 1 multiplexer. And now we are going to draw it, and we are going to first erase this stuff here to make some room like this. Okay, and now we are going to draw our new multiplexer here. So this value is going to go into that. Okay, so we have a multiplexer here, and this multiplexer is certainly going to have a control signal, and it will be one bit control, and we call this multiplexer ALU-SRC. This is what we call it. Now this ALU source multiplexer, it's going to be controlled by the control logic, and we are not discussing the control logic right now. We are only developing the data path. So we will talk about this ALU source control signal later on, not today, because today we'll be just discussing the data path. Okay, but I'm just writing it here so that you know that this is a control line that we have to control in one of the following lectures. Okay, now that's very good. So we read out we pass, or we send lower 16 bits of the instruction code to sign extender circuit. It produces a 32-bit number preserving the sign of the input number. This input goes to lower input of ALU source mux. The upper input of ALU source mux comes from RT register value, and then one of these values will be input, will go to the second input of our ALU, and the first input will come from RS. This is RS. Okay, fine. Now look, what is the third step? Look, the third step is, this is the third step. The result of addition operation should be sent to the input of data memory. Okay, so now the result of the addition operation should be sent to the address input of data memory. This is data memory. Let's write here data mem, and this is the address input of data memory. Okay, and this data memory will have two control signals. One will be called read mem and the other one will be called write mem, and we will draw them later, but they are control signals, so right now we are not worried about them because they are control signals. Okay, good. Now when the result of the ALU, the result coming from the ALU is presented to the address input of the data memory and read mem is asserted, this memory will present the data stored at that address at its output. Okay, it will present the data stored at its output. Good, very good. Now we want to send the data back to register, and in this case we want to send it to register 7. Okay, so let me also erase this stuff because I want to draw my lines here. No, it's difficult to draw these. So we have LW, then we have RT, comma, offset, and then we have RS. Okay, so this output, data output, the data coming from data memory must go to register file. It must go to register file. Now this is also 32-bit data. Once again, you see we have a problem here. We have two inputs coming together at one point, two signals coming together at one point. So what does it mean? It clearly means that we need a multiplexer here. Okay, we need a multiplexer here. So let's erase these lines and let's make some room for our multiplexer. Let's make some room for our multiplexer. Okay, good. So we need another multiplexer. So let's say that this is our mux. This is our multiplexer. This multiplexer has two inputs. One input is coming from directly from ALU, and the second input is coming from the output of data memory, and then one of these values will go to the write data input of register file. So we are going to need a control signal here. So what will be the size of this mux? What will be the size of this mux? This mux is going to be a 2 to 1 mux, 32-bit wide. 32-bit wide 2 to 1 mux. And this signal, we are going to call the signal mem to reg. This signal will be called mem to reg. Mem to reg. Okay, mem to reg signal. REG, mem to reg signal. Okay, now we are still not done yet. Actually, let me redraw this figure because I have completely run out of space, and let's move this further down. Let's erase this and also this. I'm sorry, this is the first time I'm drawing it by hand. previously what I used to do was I used to import the PDF, but today this time I thought that I'll draw the figure by hand so that you can see how each new piece is introduced in the diagram. Oh, sorry. Okay, so let me see. I also want to erase this line, but I do not have very fine eraser, very small eraser. So look, what I'm going to do is I'm going to do it like this. Guys, I'm really sorry. You know, I've never been good at drawing. जो मेरे स्कूल के टीचर ना ड्राइंग के, मुझे उनसे सबसे ज़्यादा डर लगता था, बड़ी बेदर्दी से पीटते थे और मुझसे ड्राइंग होती कोई नहीं थी। अभी भी उनका चेहरा मेरे सामने आता है, कांपने लग जाता है बंदा। एनीवे, ये मैं साइन एक्सटेंडर को ज़रा बड़ा बना रहा हूँ। ये देखें, ये मैंने किया ही है कि ये है, ये मेरा साइन एक्सटेंडर है, साइन एक्सटेंडर है, ये इसका आउटपुट है, ये दिस इज़ द इनपुट। ओके, अच्छा अब देखें, अब मेरा काम ज़रा ना आसान हो गया है, क्योंकि देखें इधर नीचे मेरे पास जगह है काफ़ी, इधर यहाँ ये इधर सारी मेरे पास जगह है, इसमें मैं अपनी फिगर बना सकता हूँ। ओके, अब नाउ लेट्स कम बैक हियर। ये हमारा एक इनपुट ALU का सॉरी मक्स का इधर से आ रहा है, दूसरा इनपुट मक्स का इधर से आ रहा है, और ये हमारा मक्स है, ये जो उसका आउटपुट है ना मक्स का, वो वापस इधर जा रहा है। अच्छा, अब इसका जो नाम, व्हाट वाज द नेम, इट्स नेम इज मेम टू रेज, ये इसका ब्लू कलर में वी हैव इट्स कंट्रोल सिग्नल। So this is a 32-bit number, this is a 32-bit number, this is a 32-bit number, and this is our mux. This is our mux. And this is the data line. Data. Okay. मुझे क्या कह रहा है? Oh, it's telling me that I have section B class. Okay. So mux हो गया पूरा. Okay, good. Now this is complete for load word. For load word, this is complete. Let's see. What was the instruction that we were executing? Sorry. We were doing this load word 7, 8, 10. This was the instruction. Let me rewrite it in a different color. Let's use purple color. Load word. This was the instruction, okay? So this is good. beautiful color, pink, girlish color. Okay, so we will have the value of RS coming here, the value stored in RS coming to the upper input, and the lower input this time it will not come from register RT, but it will come from the sign extender output, and this mux will allow the sign extender output to pass through and enter the lower input of ALU. ALU will perform addition. That addition will produce an address. That address will be presented to data memory address input. Data memory is going to present data at its output port, and that 32-bit data will go to the input of a mux, and this ALU result will also go directly to the input of the same mux. And since this is a load word instruction, we don't want to store this data in the register, but we want to store this data in the register, the data coming from memory, not the data coming from the output of ALU. Okay, so that's why we will set mem to reg in such a way that this data, it goes to the output and then it gets stored in the register file. All right, so far so good. Okay, so now I'm going to erase this arrows, and now we want to talk about store word instruction. Okay, now we want to talk about store word instruction. So what does the store word instruction do? Store word instruction, first two steps are same. First two steps are exactly same. Okay, then the third and fourth steps, they are different, because now the data will be going from register to memory, not from memory to register. Okay, so first two steps are same, but in third step we want the value. Okay, let me actually explain this in more detail. Suppose this was the instruction that we wanted to execute. Now this instruction says first two steps are same as in load word. So in the third step, write the value stored in RT register to the address I should say data memory address, to the data memory address calculated in step 2. Okay, so let's come back up here. So basically this time what we want to do is we want to get this value and we want to write it into the data memory, the value stored in RT register. So let's actually write it here. Value of register 7 goes to address obtained by adding 8 to the value stored in register 10. Okay. So now this data memory, it has one address input and then it has a write data input. This is data input and this was actually data output. This was the output port of the data memory. This is the output port of the data memory and this is the input port of data memory. So what happens is that you want the value of RT to go to the data input of data memory or input port of data input port of data memory. Okay, and since you want to write data into data memory, so you assert write mem signal to do that. So read mem and write mem signals, they will appear here. There will be one read mem signal, there will be one write mem. Read mem and write mem. Read mem and write mem. So when you for load word instruction, read mem will be asserted. For store word instruction, write mem will be asserted. Okay, so now our data path is complete for R type instructions and for load word and store word instructions. So in the process, we have added a couple of more multiplexers to our data path so that correct data goes to correct inputs. Okay. For example, second input of ALU or lower input of ALU, it can come from either register RT or it can come from sign extender output. So this completes our discussion of data path for R type and load word and store word instructions. So the next part, in the next part we will cover a branch if equal instruction. So I'm going to stop here and Azan is also coming. Okay, so oh my goodness. So there we go.